Welcome. So today we're going to go over a simple example of feed-forward amplifier compensation. And we're asked to consider the simple two-stage feed-forward op-amp shown on the right here. And these capacitances CO1 and CO2 are somehow fixed at 150 femtofarads. The intrinsic gain of these GMRO amplifiers, these transconductance amplifier, is limited presumably by the technology in which they're implemented to 10. And we're asked to select the transconductances required to ensure that the open loop gain is at least 50 up to 500 megahertz and a phase margin of 45 degrees is provided. So let's think about this problem a little bit. First of all, we're going to focus on the red path through the amplifier here, which is a second order path. That's going to provide most of our gain in band. So that's obvious. The response through that path, being second order, is going to be constant up to some frequency, and then roll off thereafter with a slope of 40 dB per decade. The blue path, on the other hand, is a first order path. That's our feed forward path through GM3. And that is going to have a lower gain since there's only one gain stage in there. But it is going to roll off at only 20 dB per decade. And so that's going to introduce this lead compensating zero into the response. So focusing on the red path first, in order to meet our gain spec, we see that the DC gain through those two stages is limited by this requirement here to be 10 times 10 or 100. So in order to ensure that we've got a magnitude response over 50 up to 500 megahertz, we need to ensure that the two poles introduced at these two nodes causes the magnitude response to dip only by 6 dB with respect to that DC gain of 100. So that'll occur when the two poles are again arising due to these two nodes both arise right at 50 megahertz, 500 megahertz, sorry. So that will ensure that each of the poles introduces minus 3 dB compared to the DC gain for a total minus 6 dB. That'll give us our DC gain. That'll give us our gain of 50 at 500 megahertz. So how do we ensure that? Well, we've got the capacitances at those nodes. They're 150 femtofarads each. So we've simply got to select the output resistances RO1 and 2 so that the time constant at these two nodes each corresponds to a pole at 500 megahertz. So there's the pole frequency, the capacitance, and we can calculate the required resistance. The transconductance, GM1 and GM2, is then determined by the fact that the gain, the DC gain of each of these transconductance amplifiers is only 10. So we can use this expression now. To calculate those transconductances. GM1 and GM2 are the DC gain 10 over the resistances. That gives us 4.7 milliamps per volt. Next, we've got to introduce the feed-forward compensation transconductor GM3. We've got to choose the right value for GM3 to ensure 45 degrees of phase margin. So if we assume that the two low-frequency poles here, these two poles, are going to give rise to about 180 degrees phase shift, then we need the lead compensating zero introduced by GM3 to give us a plus 45 degrees phase lead, and that'll give us the required 45 degrees phase margin. So if we use this expression here for the location of the zero as a function of the gains of each of the stages, we see that we can relate the zero frequency to the gains and to the pole frequency. The first pole frequencies through the red path are both located at 500 megahertz. We know that DC gain AV1 times AV2 is equal to 100. So we can now calculate what we need AV3 to be, and from that infer what GM3 needs to be. So specifically, we see that AV3, that's the gain GM3 times RO2, has to also equal 10. That means GM3 is just going to be the same as GM2. So what we end up with is situation really where the 0 kicks in, right at the gain crossover frequency, something like this. Okay, and that's going to give us the extra 45 degrees phase shift. So that's all good for the hand calculations. Let's see how it works out in simulations. We've got that entered here to our simulator. You can see the transconductances are all 4.7 milliamps per volt for GM1, GM2, and GM3. The capacitance is 150 femtofarads at each node, and the output resistance is 2.1K as we calculated. I'm just going to run an AC simulation here to see what kind of phase margin we get. So first of all, you can see the magnitude response here, the solid line. If we focus on the point at 500 megahertz, we see we've got a gain of about 34.5 dB. If you just look at the cursor value there in the bottom left corner, I know it's quite small, but 34 dB corresponds to 50 volts per volt, which meets our spec. It's a little bit subtle, but if you take close note, you'll see that the magnitude response is rolling off here at 40 dB per decade, and then it does bend slightly upward due to the lead compensating resistor. The effect of that is perhaps more obvious looking at the phase response shown here at the dotted line, where you see clearly if the phase response is going down towards minus 180 degrees, but then curves back up and approaches minus 90 degrees asymptotically. Again, that's because at high frequencies, the response is solely determined by the path through GM3 here. So let's check our phase margin. The phase margin can be observed by looking at the unity gain frequency here. It's about 6.5 gigahertz. If we go down, look at the phase response there, indeed it's at around minus 135 degrees, so a little bit more than 45 degrees of phase margin, just like we calculated. There's some slight deviation from that because the 0, in addition to changing the phase response, also introduces a little bend in the magnitude response, so it extends the unity gain frequency a little higher than our calculations assumed, but the approximations are all pretty good here. So we've also, for fun here, you can look at what happens if we use a 3-stage feed-forward amplifier to try and achieve the similar specs. So here I've chosen some values that still respect the limit that all the GMs times the Routs that they drive are all equal to 10 or less. So the assumption here is that it's a similar technology, or sorry, in this case, correct myself, all the GM times Routs are limited to only 7. So the idea here is that we're in a different technology now with a lower intrinsic gain, so we have to use 3 gain stages to meet the same spec. So we're still shooting for a gain of 50 up to 500 megahertz, but now we need 3 stages in order to achieve that. The node capacitances are all 150 femtofarads as before, and you'll see if we run a simulation here, run our AC simulation, we'll see what happens. So now, again, if you take close note, you would notice that the magnitude response is rolling off here at 60 dB per decade because it's determined by the third order path through GM1, GM2, and GM3 in the schematic. You'll also note the phase response goes almost all the way to minus 180 degrees. It's actually asymptotically going towards minus 270 degrees, but now there's 2 zeros introduced, so that again it bends upwards towards minus 90 degrees asymptotically, and the magnitude response also bend upwards. Now, if we look at the magnitude response at 500 megahertz, that's around here, you'll notice that we've still got a magnitude response of about 34 dB. So it's the same. It's about 50 volts per volt at 500 megahertz. However, the DC gain is a little lower, but that's okay. It's still meeting our spec requirement in band. And let's check our phase margin here at 0 dB crossover, the unity gain crossover frequency here. It's now lower than before, again, because of the steeper roll-off, but we've still got our phase shift of about minus 135, so about 45 degrees phase margin. So this is interesting. And another thing I'd note that if you sum together all the transconductances here, all the GMs, you've actually got a lower total transconductance, despite the fact that there's now 5 transconductances than what was required to meet the same specs with a two-stage amplifier. Even though we're in, a technology with a lower intrinsic gain, we're able to go to 3-stage feed-forward amp, and assuming that all the bias currents are related to the transconductances, proportional to the required transconductances, then actually you may end up with a lower power consumption for this 3-stage feed-forward amp, meeting similar specs, in spite of the fact that you've got lower intrinsic gain and you need more stages. So that's it. Hope that helps you understand this feed-forward amplifier compensation.